Okay, let's begin. So, warm up. How do you guys feel about the answers that are up there? I haven't looked at them yet. So for A, that's geometric, yes. It's not obvious maybe right away when you look at it that it is, maybe. I mean, I tried to mask these as much as possible by making them terrible with fractions and stuff like that. But in the end, no matter how sneaky I am, as much as I try to make it look like it's not geometric, how can you tell that a sequence or a series in this case is geometric? For sure. Like, what test will always work? If it ends up being geometric, then what must happen?
You divide one term by the last one, then it'll be the same number.
Yeah, if you divide one term by the previous term, you always get the same number. That's like the definition of a geometric. So in the end, you shouldn't be like, I'm really having trouble figuring out whether it's geometric or arithmetic. I know it's sometimes hard to like look at it and see that, but you should at least be able to do that and like then walk away just knowing one way or the other. Same with B too, right? Is there a way you can test what kind of series this is? Who did this? Elvin. So what's going on there?
It's arithmetic.
And what's the rule, or what's going on there?
You add one.
Yeah, it's adding a fourth each time. Again, I'm trying to make it maybe not so obvious by the numbers, but again, it's arithmetic, so don't. Hopefully you see that. And we already established that all arithmetic series diverge. On the first one, sorry, I didn't say. Is that the right sum?
Yeah.
Okay, good. Let's move on. Part C diverges. What does AL stand for? Alex. Can you explain why?
Because the ratio is greater than 1, or the absolute value of the ratio.
And to know that, you had to know that pi is greater than 2.
Yeah.
Good job. Okay. Here's a tough one that I gave. I think this appears on some series problem that I gave to my calculus students or something, but just for fun, as a review. But you can do it right now. Here's a geometric series right here. 7 pi over 22, all of them again.
That's a convergence.
Good question here. Does that converge or diverge? Yeah, you might need your calculator on this one.
Mr. Chase, isn't 7 over 22 an approximation of pi?
It is an approximation of pi. Is it pi?
No. 21.99.
So yeah, so it's like just by looking at this, yeah, the fact you even have to go to your calculator to decide whether this is bigger than or smaller than 1 is fun. Like the fact that you have to go to your calculator is fun. So what's the answer? 0.9995. That's what the in parentheses that comes out to. So what do you say then?
It's 1.
It does converge, but just barely, right? Like that's cool. So that would be fun and mean. This was not so mean, but I think you can do that even without a calculator. And on D, Anna, can you tell me as a fraction what that is? Yeah, and how does that come about? How do you know that that's the case? Without a calculator even, how would you figure that out? I mean, I know, or maybe you just experienced, you've done it, but do you remember how we did it? Well, I guess we didn't do it in class. What kind of series is it? Yeah, I think we maybe didn't get to an example of that. I forgot. In my other class we did, but it is geometric. Yeah. What's the first term? It's 0.53. And what's the common ratio? Yeah, it's 1/100. And if you simplify that, I might multiply the numerator and the denominator by 100. You'll get 53 over 99. Give it a try. Isn't that cool? I just want to make sure we understand that like math works, and that this is in fact a geometric series. And yeah, I don't know. Good stuff. Anything else you want to say about the warm up or? From Thursday. That provides a pretty good summary of what the kinds of things we thought about on Thursday. So let's talk about infinite series of other kinds today too. That would be our goal, is to start moving into not just arithmetic and geometric infinite series, but any kind. So we're going to start by reviewing everything we did on Thursday. There it was. There it is. We did the paper monster thing. That was so fun. Yay. And we looked at, oh, we didn't look at this picture. Here, this is how we should open today. Look at that picture and tell me why that's cool. Wait. Give everyone a second to think about it. Don't tell anybody yet why it's cool. Give everyone like 20 seconds to think about it. What does it say to you? Maybe there's something infinite, and I hear the word infinite series, but is that the whole story? Man, what does it actually say? Think about it. Don't tell it to me yet.
But that one clearly ends at a certain point.
Oh no, the resolution becomes too blurry for you to see.
Oh wait, I forgot to take it.
Okay.
I forgot.
So, could someone share? I know a lot of people have said something about infinite series, but I'm worried that actually maybe you didn't see the profound thing here. Why is it cool? Does someone want to share out? Raise your hand. Haley, what do you see? Okay, I see that. There's an infinite sum result that's available to us by looking at this picture without actually like having to use the geometric sum formula. You see it? Yes. Yeah? What about 1? How do you know it's the sum? So a half, the question I guess would be, what is 1/2 plus 1/4 plus 1/8 plus 1/16, etc.? And the answer is 1. How do you know that without the geometric sum formula? Yeah, I mean, I think it's right before your eyes. That's the whole point of this. But I just say it. I say it though.
Half plus half equals 1.
Yeah. So the area of the square is pretty easily computed as being 1. Is that clear? Without having to think about infinite series. But then this infinite series also makes it clear that that infinite series equals 1. There are 2 ways to compute the area, and they must agree. So that's cool. You can also check the geometric sum formula works. All right. So let's begin our thoughts about series that are not arithmetic or geometric, that are infinite, with something called the nth term test for a divergence. And these are on the handout I just provided for you today. I've given you like all the tests there. And before I read this out loud and have us think about this, can I just remind you, I think this is our task maybe every day, is to just remind ourselves that there are 2 limits happening every time we're thinking about this series stuff. Remember that there's the limit of the terms themselves, right? Before we ever talk about adding them up, there's the limit of the actual terms themselves. And for like a geometric series like 0.53 repeating or whatever, and we saw that a second ago, 0.53 repeating, we were working on that one. The terms themselves go to 0, do they not?
Yes.
Because eventually we have terms that look like, the terms look like 0.0000000053. So if you look at an individual term, out at infinity, the terms are basically 0. And I want to make sure we're clear, really clear on that. That whole conversation is the limit of a sequence. We also have the notion of the limit of the sum of those things. Now, finally, I ask you, add those things up, and what do you get? And the answer is different. It's of course not 0. It's 53.99 or something. Okay, so let's make sure we have those really clearly held in our minds. There's a limit of a sequence and a limit of a series associated with any given problem that we might be thinking about. With that in mind, let's think about the nth term test for divergence. Take a second if you haven't already to read it. And then think about why this would make good sense. If I tell you, hey guys, I have this series, it's not necessarily geometric or whatever, but the terms themselves of my series get ever close to 2. Now I have not at all asked you anything about the sum of this series, of this sequence yet. It's just a sequence that out at infinity, if you plug in like the millionth term, it's like 2-ish. And the millionth first term, it's also 2-ish. The billionth term, it's 2. It's basically 2. At the beginning it wasn't maybe, but out at infinity it's basically 2, 2, 2, approximately. What do you think happens when I now ask you for the infinite sum of a bunch of stuff, and then eventually that goes plus 2, plus 2, plus something that's approximately 2, plus something that's approximately 2? Do you have any idea about its convergence? You can think about, again, in terms of partial sums, what will those partial sums look like? Would they be getting closer to a number? What do you guys think? Yeah, and so this is what this says here. Is the only way for it to have any hope of convergence is if the terms themselves go to 0. can't be true that we are adding something like 2 continually out of infinity. Out of infinity, we better be getting increasingly like it's like we're just adding 0. And I should maybe before we do this problem, I should also caution you, and I can't make this caution strongly enough. The converse of this is not true. And what would the converse be? Someone might say, what? Right, and that's false in general. Did you hear what he said? So just be careful. In fact, I tried to make this, I used to just call it the nth term test, but I'm trying to make it more and more clear for my students. This is the nth term test for divergence. There's never, ever a time where you'll say, this series converges by the nth term test. No. No. The worst case, the best thing that could happen there is if the terms do go to 0, you need to test other things. It's inconclusive. However, if they don't approach 0, then the conversation we just had makes sense. It definitely diverges. So this is one, for example, that is not arithmetic or geometric. So we want to ask this question about this series. Even though it's not arithmetic or geometric, can we still say something about its convergence, the series itself? Yeah, Helly.
How does something not be divergent and then also not be what is that?
Oh, well, we just don't know. I mean, we need to apply some other test. This test isn't strong enough. It is either one or the other, though. Convergent or divergent. It's just this test isn't strong enough to tell us which it is.
So if it shows divergence, then it's not convergent, but if it doesn't show divergence, then it's still convergent.
So the direction of the implication here is if the terms don't go to 0, then it diverges. But is the converse true? That doesn't say anything about the converse, right? That's the thing. So if you want to conclude something converges, you can't use this. So let's talk about this. Not talking about the sum yet. What do the terms of this go to? It's nice of me to give you the rule, isn't it? Could you have come up with the rule if I hadn't provided it? I think you should be able to do that, but just search your heart on that one. Okay, but given that I've given you the rule, what is the limit of the terms themselves? The actual terms themselves. Like, what does this look like? The millionth term is approximately what? What?
0.
Nope. Yeah, it's approximately 0.5, approximately 1/2, isn't it? Like if you plug in 100, you get 100 over 199, don't you? So increasingly, this is the case where we're adding, out in infinity, it's like we're adding 1/2 plus something that's close to 1/2 plus something else that's close to 1/2, etc. So what do you say about the actual series now? Yeah, this diverges by the nth term test. And you should maybe say why. Well, it's because the limit of the terms, that is the limit as n goes to infinity of this term, is equal to 1/2, and I think that's not 0. So, is that good? So do say that, right? Don't stop with the word diverges. Please justify on every one we're going to do today. I'm going to ask you to actually justify using some test and apply whatever the criteria for that test are. Here I've done it in this set of parentheses. So if I haven't said it strongly enough, there it is again down at the bottom, right? This can't be shown. You can't show convergence by this. And that might, this is territory that's really dark for us right now. It's still the fog of war is still upon the land, right? We're charging out into this unknown territory, and it's really, this is hard to understand what's actually being done here. What are we doing, adding these things up? So, some more examples is what we need. You might think, can you show me, Mr. Chase, an example of a series that has the terms going to 0 and yet diverges? Wouldn't you like to see one?
Yeah, it would just be if it starts really high and then subtracts small amounts.
That
Technically approaches 0 eventually.
No, I mean the terms go to 0.
Oh, okay.
Yeah, you mean. I'm going to show you the series. Amy, what's up?
So, when on a test or something, do you have to write this off in a parentheses?
Yeah. Yeah. Everything I wrote is a good thing for you to write. Okay. So, are you ready? This is the classic go-to example. There might be some others, but this is called the Harmonic Series, and actually I'll introduce a couple different interesting series to you. There's a pretty graphic that makes you happy to see it, I guess. I don't know. This is in a box, but it's also in your paper. And in general, we call these the P series. The first one where P is 1, that is, we're looking at series of the form 1 over n to the P. So, for example, the series 1 over n to the 4th or something, or the series 1 over n to the 1. So do you agree that this is that series? We're just adding up 1 plus 1/2 plus 1/3 plus 1/4, etc. And it turns out that diverges. And there are a couple ways, nice ways to show that. But for the sake of time, I won't explain completely right now why. But here's a nice thing you could try, though, if you're not convinced. On your calculator, you can start adding this up. I didn't share this with you before the quiz. Maybe I should have. But well, there is a sum feature on your calculator. And if you have an old calculator, it goes like this: 1 over n, and like alpha n, from 1 to, you want to add up the first 100 terms. There you go. And some of you actually, I think on the math menu, actually have, if you have a newer calculator, you actually have a summation notation thing. And then you can just type it in exactly as it says here. N equals 1, 1 over n, and 100. So on the old calculator, you have to do this first thing, and you can do that by finding those two commands on like the list menus. So anyway, you can give it a try. Add up the first 100 terms. And our claim here is that you might add up the first 100 terms and see that, hey, you know what, I think this never goes above 10 or something. I don't know. You claim that a 10 is an upper bound for this sum. Well, it'll never go, even if I have 1,000 terms, it'll never go above 10. So that must be the sum. Well, I can find you a place for this series after which it is actually, the sum is actually 10. It's really, really slowly diverging. So feel free, 100 doesn't get you very far at all on this. Try 1,000 and wait a few minutes on your calculator. Try and, your calculator might break if you make that number too big. But yeah, that's on that's under second list. What is it?
I don't even know.
Second stat, which is the list menu, and then it's like ops or yeah.
Ops. But then you just go to.
But like I said, this, I think a lot of the if you have a newer calculator, I think you can even enter this. This is on the Mac menu, isn't it? Is it directly on the Mac menu? So you don't have to enter the crazy thing. I'm used to the old calculator, so whatever. It's not imperative that you do any of that. I just thought it would be fun to show you that. If n happens to be 2, it converges. That is, if we're adding up the reciprocal squares, it converges. Wait, what? This is, like I said, this is where we're in the fog of war here. Our intuition is failing us here. In all of these cases, regardless of what p is, we have something that the terms go to 0. For all of these, the terms themselves are going to 0, right? For this one, for the next one I'll show you too. All of these, no matter what p is, this goes to 0. But sometimes the series converges, and sometimes the series diverges. I've claimed just now that this converges, the sum of the reciprocal squares converges. Now, you might then wonder, what does it converge to? I hear you say. Now, in this class, it will not be expected for you to, if a series converges, it will not be expected that we say what the sum is. All you'll have to say is that it converges, and then walk away. Unless it's geometric, in which case I would like you to get the sum, because we know how. But in general, like the problem of summing an infinite series, that's just like a general infinite series that isn't geometric, is a hard problem. And that's like a technical term. Okay? So this one happens to converge incredibly to pi squared over 6. This is what it comes out to. Not something that will ever be tested. I just wanted to include it because it's super interesting. And Euler is the man. Euler's birthday was on Saturday.
Oh,
He's dead, but, you know. Whatever. Okay. He's the man, though, and he determined that it was true. He's the first one, I think, to be credited for that result. But and the other reciprocal powers have equally interesting values they converge to that include the number pi. Yeah. I didn't actually prove that just now, did I? But if you go to my math blog, I have a link to 12 different proofs of that fact. One of them we'll share with you in calculus next year. They don't all require calculus though. There are some pretty nice ones that maybe tomorrow, because we're going to do some more tomorrow. I'll share a proof of the fact. Right now, I did suggest that you could just like start adding it up and see that it never, like, if you think it never goes above 10, add up more terms. You'll see it does go above 10. Careful, you'll have to add up a lot of terms though. Yeah. Alpha n. There's nothing special about n, by the way. You can use any letter. Yeah, you can use x. So you need x here too, and here, comma x. Do you have it? Okay. You know, do what you can. Oh yeah. So and then did you see this one down here? Right. To be clear, sorry, we should go back and up and actually visit the result again. We didn't actually read it. So the point is, if p is 1, then it diverges. Or if p is anything less than 1, like down here, p is 0.5, that is some of the reciprocal square roots. I don't know what's going on there. Oh, no, that's 2. That's okay. We're okay with that. I think I understand. Then, with diverges, if p is greater than 1, that is strictly greater than 1, then it converges. So even if it's 1 over the sum of 1 over n to the 1.1 converges. It converges very slowly, but it converges. Okay? All right, so that's a nice thing to have in our back pocket. That truth. It is true. You're begging for a proof. So I understand. We'll come back to it tomorrow. I promise. Let's take a second to read. Even 30 seconds here to read number 4, the direct comparison test. It's on your sheet. I have it exactly as it appears on yours. And it's really 2 sentences. You can read them as completely separate sentences. And then we'll talk about what it means in a minute. Process it. I'm going to tell you in a second. All right, so what does the first sentence say? Let's be clear. Let's worry about the second sentence in a second. I have, you guys, right now, I have a convergence series. I've worked with it for years. I love it. I know it. It converges. Okay, just take my word for it. Now you come up to me with a brand new series that none of us have ever talked about or thought about. Your series, keep in mind, my series is a convergent one. Remember? Your series is term by term. Every term of your series correspondingly is less than my series. What do you think must be the case about your series? It converges too, right? Term by term, yours is less than mine. Mine converges, yours must too. Should just make kind of obvious sense. The second statement should make just as clear sense. Okay guys, I have this series. It's known to be divergent because I've just worked with it for years and I've established already using other means, so I know it's divergent. You come to me with a brand new series that we've never thought about. It is, term by term, bigger than my series. What do you think is true? What has to be true there? Mine diverges, yours is always bigger, it must diverge too, right? If you understand that, then we're done here. Now, there is one other small thing to say, and that is what happens if we have a convergence, I have a convergence series. and you come to me with a series that's always term by term bigger than my series, well, I can't really make a conclusion there, right? Does that make sense? The other two cases I definitely can. Charles?
So does that have to be bigger or less than the corresponding terms, like by a certain amount each time?
Not necessarily, no, no. I mean, in fact, they can be equal to, if you like, right? As long as you're always inside my series, I'm converging. If your series is always inside of mine, then I think we're good. Yeah, Sue.
Does this also work for negative?
A little trickier. Yeah, I mean, if all the terms are negative, then I think we can talk.
Yeah.
And then we can change inequalities to suit ourselves. Things are a little weird and complicated when we have alternating series, and we won't talk about that too much in this class, particularly. But yeah.
What series do we know?
Yeah, that's a great question. How about some of these? All right. So, which one from that last slide reminds you of this one? It isn't it, but which one would remind you of this? Does that help?
Yeah.
Yeah, doesn't it seem a little bit like 1 over n to the 4th? Which I know something about. Which one is that? Because it's been a while. That last slide. What does it do?
You see 1 over x squared.
Does it converge or diverge? It converges. So here's what I'm going to write. Since the series 1 over n to the 4th, that is from n equals 1 to infinity, converges because Mr. Chase told you so. Because it's p equals 4, which is greater than 1. And if p is greater than 1, then it converges. So I would write that. And, okay, wait, hold up. We need to stop here. What do we want to conclude? We're hoping that this is term by term. Each term is, we think this converges, don't we? It is always, we'd like to claim maybe that this is less than our series. Is it though? Can someone, I just want to make sure that we're, what's the reasoning there? Why can you convince me of that? I think I could plug in like the 11th term, I could figure out what it is and see that it's both, in both cases it's less, yeah, it is less than that. Okay. This is bigger than that. In general, just from the algebraic form, can you give me a justification for why this is definitely, this is always definitely bigger than this? Matthew, take away.
Since in the denominator of the new one, 3 is added, then that inherently has to be a smaller number than if it was just 1 over n.
Yeah, I'm thinking about fractions. If you make the denominator bigger, then the fraction gets smaller kind of idea, right? Yeah, I think I'm convinced now I'm going to actually write it, okay? If you are. And 1 over n to the 4th plus 3 is less than 1 over n to the 4th for all the n in consideration. And all the n are that I'm talking about are n equals 1 to infinity, right? The series that we're looking at, that is the sum from n equals 1 to infinity of 1 over n to the 4th plus 3, converges also. By, how about we just say DCT? Do we all know what that means? By direct comparison test, yeah. So I would invite you to write that, please, if you'd like to, because here it's pretty clear that I'm talking about the direct comparison test because the slide says it. But in general, we'll be doing a whole bunch of different series, and we need to know, say which test you're using, because we've got a bunch of tests that we'll be sharing here. Say which one you're using. And that's what I'd like to see, really. The work I've just shown is what I'd like to see. And look, really, if you're missing even any one element there, I think you haven't really said the whole argument. Okay. Let's skip this one because I just think it's boring. Okay, let's do this one here. So stare at it for a second and then determine what you're going to do, or what we're doing. Which do you think it is? Is it convergent or divergent? Which series are you comparing this to? we already looked at. What does it feel like? If you haven't noticed, like basically we're always going to be going to one of those p-series, right? That's why we get the slides in that order. There's no reason it has to be one of those, though.
I won't make the same mistake. Sorry, Logan.
Did you do it? Stay with me here. So which one does this feel like? How about Kate? Which one do you think this feels like?
We have more.
You don't know?
If you like some.
What about Alex H? Which one do you think this feels like, Alex H?
No, it feels like the P series one.
Which one?
The one
P equals what?
when P is 5.
I'm looking at this one, sorry.
Oh,
But
okay, sorry.
good job up here. That's correct. Good job. All right. Can you do this one on the fly?
Oh,
We're going to skip this one.
I haven't, what, so P would just be 52/3?
Yes, I tried to make it tricky, but I wasn't very good at making it tricky. Okay. I could make it trickier. But this is good. All right. Here we go. So n is so since to the 2/3. Wait, which does this do? Am I going to fill in the word? What word goes here? Diverges or converges? Why does it diverge?
T is smaller than 1.
Because p is 2/3, which is less than or equal to 1. And now what else do we want to say? This time this diverges, so what do we want to hope is true here? Yeah, we want this to be greater. It is, term by term. So, and 9 n to the negative 2/3 is always greater than 1 over n to the 2/3. Again, for all n greater than or equal to 1. So this series converges too. By the direct comparison test. Okay. Next thing to study on the sheet
Divergence.
is the limit comparison test. We're not going to get to the ratio test today, which is sad. That's okay though.
Divergence.
That's what I meant. You know what I mean. Diverges. What she said. Okay. But study now the next one, which just says the limit comparison test. And it's just one sentence, but read it like 4 times. So you can figure out what it means. Yeah.
Why is it 2 over 3 instead of negative 2 over 3?
Rule of exponents.
So you take that P series and just like
Start a little straight, yeah. Like.
9x to the 2/3.
All right, so let's see if I can say something about this one at least and do this problem before we leave. That would be a good goal. All right, so what this says is, keep in mind the an and the bn in this expression, they look small, but in the end they're actually the whole rule for two different sequences, okay? And the question is, if I take the limit of these expressions as they go out to infinity, and the one on the bottom is growing faster than the one on the top, what does the limit come out to be if the one on the bottom grows really big, really fast? Yeah, it goes to 0. What if the one on top grows faster? It goes off to infinity. But what if they're the same? What if they grow at relatively the same rate? It goes off to 1, or possibly some other constant, right? And that's what this is saying. If you can identify 2 series that grow at the same rate, and this is like the rigorous test for that, then if one of them converges, the other must too, because they have the same relative growth rate. if one of them diverges, either one, then the other must diverge too. Okay, so the way this goes is like this. See if we can do it before the bell. Since, what do we want to compare this to? 1 over n to the 4th, how about? Converges. Because p is 4, we've already done this before, which is greater than, strictly greater than 1. And the limit as n goes to infinity, here's the stack of 1 over n to the 4th divided by 1 over n to the 4th minus 3 equals, does that equal 1? Equals 1, and 1 is not infinity or 0. This converges too. By the limit comparison test. So that's how this goes, and it works just as well for divergence too. If both theories, if we get one and one of them diverged here, then it would also, the other one would diverge. If you get 0 or infinity, you pick the wrong thing to compare it to. Try again. More tomorrow. I love you all. Bye.